of two reactants, and they have given you this data. This is the one that we tell every single time before we get a rate of the rate equation. Rate equals to k watt. Okay, we will get the data from your experimental results. And when they mention experimental results, this is one of it. Okay, experimental results can be presented to you in form of table, or they can also present to you in form of graph. Okay, so you need to be you need to actually know when to use. Okay, the graph, I think you should know by now, so it's okay. I can actually draw the graph, sketch the graph for you. So if you have a graph of concentration against time, okay, we have one graph which is going to be something like this. Okay, concentration decreased by time like this. Or we have another graph that is going to be something like this. And we do have another graph that will go like this. Okay, so please take note. This is concentration against time graph. If you have, okay, but please take note as well. Okay, if I make it bigger, this is going to be for zero order reaction. The one that is steeper, that's going to be second order reaction. This is going to be your first order reaction. Okay, so if I want to actually draw another graph, which is very popular, which is rate. Okay, rate against concentration. Now this graph, okay, we have a situation where the rate can be constant. Now if the rate is constant, that's going to be your zero order graph. Okay, so zero order graph, this is going to be zero order. Okay, we also have, okay, second order reaction, which is going to be a quadratic graph. Okay, second order. We also have a straight line graph, okay, which is going to be your first order. Okay, please remember this. Okay, you can actually be given any of these graph. I think the difficulty will be if they give you a concentration time graph and they give you a curve, then you need to do some additional work to find out whether it's actually first order or second order. Okay, in order to do the additional work, so Charlton, can you tell me how do you differentiate first order and second order when it comes to concentration against time graph? Charlton? Both of them are curved. So how do you differentiate?
Draw tangent, right?
By checking the half-life.
Oh yeah, half-life.
Okay, by checking the half-life. Okay, so if you have two curves, okay, you need to check the half-life. If the half-life is constant, okay, if the half-life is constant, please take note, it is going to be first order reaction. Okay, constant half-life is going to be first order reaction. Okay, for second order reaction, the half-life is going to I think it's going to decrease. Yeah, the half-life is going to decrease. If it is going to be zero order, the half-life is going to increase. Okay, please take note. But if it is constant, then it's going to tell us it's going to be first order. But coming back to this question, we have this experimental data. We need to find out. They have given you two reactants over here. You see this. There are two reactants. I need to find out, okay, whether NO and O2 really affects the rate. Okay, and how to do that. Okay, like for example, you compare the experimental data. For example, if I have these two, okay, they are constant. Experiment 1 and 2 constant. But I can see that when the concentration of O2 is doubled times by 2, okay, I can notice that this is also times by 2. Okay, if it is double and also double, then it's going to be first order reaction, okay, with respect to O2. Okay, so first order reaction with respect to O2. No need to put 1. It's understood. Okay, first order. Now, I need to actually find out different experiments that I can choose so that I can actually compare for NO. But in order to do that, I must make sure my O2 is constant. So this one is constant. Okay, this one is constant. So when I see like from here to here, okay, I see this one is times 2. I want to see whether from here to here is times 2 or not. Okay, or times what? Okay, is it times 2? I think 8 times 2 supposed to get 16. I don't get 16. But I think it's times by 4 because why 8 times 4 is going to be 32. And then I can see roughly it's 10 negative 2. It means it's times by 4. So this one is going to be when you times 2, then it's actually something similar to 2 to the power of 2. Okay, so this is going to tell us that this is going to be second order. Okay, like just now when you times by 2, okay, times 2, this is also times 2 because 2 to the power of 1. So that is actually first order. Okay, so this is going to be second order with respect to NO. So you put second order. As simple as that. Okay. So here, use the data in the table to determine the order. Okay, you have the order. Please tell the order. Okay. And then you need to show your reasoning. Now, some students, they forget to actually tell the reasoning. The reasoning is you need to compare. Okay, one, reason, yeah. So reason is going to be by comparing what experiment and what experiment. Like for example, experiment 1 and 2. Okay, when the concentration of NO is double, okay, sorry, when the concentration of O2 is double, okay, so what happens to the rate? The rate is double. So you tell first order with respect to oxygen. You need to actually include this. Okay, I think please take note of this. And then the second one for the experiment 2 and 3. Okay, when you increase the concentration of NO, okay, when this one is double, the rate is the rate becomes times 4 or 4 times the rate. Okay, so therefore it's going to be second order with respect to NO. So you need to mention all this. Then only you will get the full mark. Okay, take note of this. Now, calculate. Okay, calculate the initial rate in experiment 4. Okay, this one, okay, can you tell me how to do this without calculating the K? You should not calculate the K yet, okay, because you calculate the K over here. So Justin, can you tell us how do you actually calculate how do you calculate the rate for experiment 4? Justin?
I don't know.
Yeah. Or you want to share your screen also, you can do that. I will actually allow screen sharing.
I use K, sir.
Okay. You want to share your screen?
No. I use K for this. I don't know how to find without K.
Now, please take note, you cannot use the K. Aneta, did you use the K? You cannot use the K.
We divide the 0.036 with 0.02 and then multiply by 4.
Okay. I will put it this way, yeah, because I will try to, like, for example, we know what is going to be the rate times by what and so on. Like, for example, what I did was, when I see 0.96, okay, this one is 0.32. Maybe I'll select experiment 1 and 4, okay. What happened is now there's nothing is constant, okay, but I have found out, okay, what is the order. So from here to here, okay, when I times by 3, okay, with respect to NO, I found out it's second order. It means that from here to here, I need to times by 3 to the power of 2, which is going to be 9. I need to times that with 9, which, what is that? This one, okay. Now, this one, when I times by 3, okay, we know that this rate is going to be first order. So I need to also times by 3. Okay. So what happens is I need to know that this one, the value that you have over here, must times with 3 to the power of 3 actually, the overall order. Okay. So it's supposed to be 3 to the power of 3 is going to be 27. So the answer will be 4.08 times 10 negative 3 times 27. You calculate and see whether the answer is the same as Justin's answer. Okay, Justin have calculated earlier, okay, using K.
Sir, sir,
Yeah.
if we use O2, can or not?
If you use
O2.
O2, what do you mean? I cannot understand, Aneta. If we use what?
So O2 is first order, right? And then, so we multiply the initial rate 4.08 times 3. And then, yeah, times 3. Because we multiply from 1 to 4, O2 is multiplied by 3, right? So the initial rate times 3 can, right?
But the NO is also changing, right? It means you are using which experiment, Aneta? Are you using experiment 1 and 4?
Yes, but we only use O2, cannot there?
Cannot. Because here, you see the one that is changing over here is not only O2. Because you see, according to our rate equation, your rate is dependent on O2 and NO. That is what we have determined earlier. So if the rate is, let's say, for example, you found out that NO is 0 order, then you can ignore the NO. But now you cannot ignore because the rate depends on NO and O2. So this one times 3, this one also times by 3 because you can see over here there's a different, 2 of them are changing. So if 2 of them changing, you need to combine. If you do, then actually the best answer is to actually use K. But in this question and many past year questions before, they do not want you to use the K to calculate. It means the best way is to actually find out what is K and then you come up with an equation and then try to calculate the rate. That is the best way. Okay, but here they don't want you to do that. Jody, what's the answer? Don't know where I put my calculator. Oh, it's here. I'll calculate for you guys also. 0.08. Justin, and my answer 0.11 is the same when you use the K. Jody, Charlton.
Yes.
Yes.
Right. So actually, please learn about this. Okay. If you use this, you do this, then you come back over here. They will not give you the mark for your working. Okay, you will lose the mark for working. You will get the mark for answer, but you will let's say this is 2 marks. Okay, you will lose 1 mark if you do this and then come back here. Okay, it's not suggested. Now write the rate equation for this reaction. Okay, now the rate equation is going to be, because we didn't calculate the K yet, so it's fine to say rate equals to K O2 NO to the power of 2. Okay, so it's fine to keep the K. But if you calculate the K and put the K in, okay, I'm not sure whether the examiner will give you the mark. If I mark this, if I have already deducted 1 mark here, I will not deduct here. Okay, but some invigilators, some examiners, they're very stingy with the marks. They deduct here, they deduct here. Yeah, so it depends. This one will be always 1 mark actually. Okay, so if you start with a strict examiner, okay, you won't know who are they. Okay, if you get stuck with that, yeah, you will lose 2 marks actually out of this 3 marks question. This total will be 3 marks. Okay, anyway, use the results of experiment 1, okay, to calculate the rate constant for this reaction. So they ask you to use experiment 1. So we will use this experiment 1. Rate is 4.08 times 10 negative 3. Okay, rate is mole dm negative 3 per second equals to K. O2 is 0.012. 0.032 to the power of 2. So K 4.08 times 10 negative 3 mole dm negative 3 per second divided by mole to the power 2 dm negative 6 mole to the power of 3. Please check. Are you getting the same answer as mine? Okay, correct, Victoria? Justin?
Yes, sir.
Yeah. So please check. Okay, what I wanted you to learn over here is this one. Every year, not every year. I told you this one is coming at a frequency of 3 year once or sometimes 2 years once. Okay, 3 years once means if you're talking about paper, our paper is paper 4.2. Okay, so if it is 4.2, then for that paper 4.2, every 3 years there will be one reaction kinetics question. But for different variants, okay, for every 2 years, I think once, okay, the frequency is different. Yeah, so different papers, if you're looking at it as a year, then it's actually coming up, okay, quite frequently. Yeah, so please take note. Okay, here I wanted to actually talk about this Maxwell Boltzmann's curve. Okay, please find out from the textbook. Okay, this one, the Maxwell Boltzmann curve will be like this. Okay, so this one is going to be what is the axis, Aneta? This one should be
the X is energy, the Y is number of molecules.
yes, number of molecules. So if I want to actually, this one is going to be, let's say T1. Okay, they say T1 is lower temperature, T2 is higher temperature. So let's say I want to draw for higher temperature. Higher temperature, please remember this, the graph will become flatter and go to the right. Okay, why? Because when you have higher temperature, they start to get more energy. Okay, of course, more energy is towards the right hand side. Okay, so most of the like for example, if you have this particular point, yeah, so it means there will be more particles having more energy now. So if this is the particular point, more energy now. Okay, something like that. So that's why the graph went somewhere like this, and then they will go like this. Okay, let me draw properly. Okay, something like this. So this one, okay, I just want to actually double check also. This one is T2. This is the other one is T1. Now, what is going to be what information can you get from the area under the graph? Jason, what do you get from the area under the graph?
Total number of molecules.
Yes, total number of molecules in the system. So do remember the area under the graph for T1 and T2, they are the same. Okay, they are the same. So why to explain why the peak, okay, the peak is actually changed now. It means that last time, okay, there are a lot of molecules having this particular energy, but now most of them actually have higher energy, but the number, okay, is going to be decreased because what happened, the graph becomes like this to become something like this. So it means there will be more molecules, okay, having more energy. So the graph will become a little bit flattened. Okay, that's the reason. Yeah, so it will go towards there. Okay, so let me. So here they say state and explain using your diagram the effect of increasing the temperature on the rate of the reaction. So here they say using the diagram, so we need to tell what is the effect of increasing the temperature of the rate of on the reaction. Okay, so temperature increase. Okay, temperature increase, the rate of the reaction will increase. Is that enough? Victoria, Lavi, temperature increase, rate of reaction will increase.
The collision, yes, sir.
Yes, but again, I think they want you to use your diagram. How do you use your diagram? Justin, you want to try? I think when you want to actually refer to the rate of reaction, in this case, you have to actually talk about activation energy. Yeah. So let's say this is going to be your activation energy, the minimum energy. Yeah. So here, okay, if you put here, there will be this amount of particles, okay, that can actually form a reaction. Okay, collisions will be there, but the collision that gives you successful collision, which is going to be the reaction. Yeah. So now, because of that, you can see that if I use the second graph, I will have more number of molecules having activation, more than activation energy. Yeah, this is what they say, use your graph. Okay, so here what you need to do is, okay, when temperature is increased, okay, there will be more particles having energy greater than activation energy, where they will collide successfully. Okay, this is supposed to be mentioned over there. Okay, so here if you didn't mention about activation energy, you didn't mention about more molecules or more particles having over there, you will lose a lot of marks. Okay, please take note. This one I don't think so we need to discuss. Okay, please actually I'll just write down one of it. Yeah, so here they say rate is first order with respect to NO and F2 first order. So it means that your slower step must have NO and F2. Okay, this is step 1 of slow step. And do remember 1 1 means this one must be 1, this is also 1. Yeah, to give you something. Okay, so let's say I just put to give me NOF2. Okay, and then I need to eliminate NOF2. Okay, I need to eliminate NOF2. So I have 2 NO, so probably react with another NO. Okay, to give me something that I want, so maybe 2 NOF. Okay, so I check and see everything okay, so I just put this is fast. Okay, so the rate determining step, this is the rate determining step. Okay, please take note of this. Okay, refer to the video. Okay, I think we had a very